Let's take a look at example 2.2 from our text. In this example problem here, they tell us that we have a spring, mass, dashpot, single degree of freedom system with a moving base. So the moving base is going to be important in this here. You can see we have a given diagram up here, and they want us to use the D'Alembert force method to determine the equation of motion of our mass m right here in this figure, assuming that the damping force of the system can be represented by a linear viscous dashpot as shown. They want us to assume that the support motion, or z of t here, is also known, and they tell us that when u is equal to z is equal to 0, the spring is going to be unstretched. So now that we've had a chance to read through that problem statement, understand what they've given us and what they're asking us to solve for, the next thing we want to do is create our setup page. So on this page, a couple of key things we want: any given diagrams, given information as far as our variable names, and what they're asking us to solve for. So we put all that information onto this one page here for our setup. So we have our example problem 2.2. We're given diagram here. We have our mass, we have our damper, we have our spring, we have our external load P of T, we have our displacement U and our displacement Z of the moving base. So that's the key thing here, is we have a moving base on this here. So we're going to consider this two different ways as we solve this problem. What do they tell us in the problem statement? Well, they give us our mass is m, our spring constant k, external load is P of T, coefficient of viscous damping of C, displacement of U, and our support motion here, Z of T. So we do have the special case that they tell us in the problem statement that when U is equal to Z is equal to 0, this is when our spring is unstretched. Now, the next question is, what are they asking us to solve for? They want us to solve for the equation of motion of the mass. So they tell us what method they want us to use, so we can go back to section 2.1.1, our textbook on page 22, and we can find our equation, given by equation 2.3 here, where we have F sub I is equal to negative ma, where F sub I here is our inertia force. So this is what they want us to find. They give us how they want us to find it, and we can reference that key equation there back in our textbook. So now that we've had that opportunity to create our setup page, we can reference back to that as we need as we're going through the solution to our problem. The next step is actually to start the solution. So the first thing we want to do as we start the solution to this problem is we want to draw out the free body diagram of the mass and include the inertia force along with the real forces. So that's what we do here. Draw out our FBD, our free body diagram. First thing I want to do is redraw my initial given diagram here. If you're solving this on your own or in a homework problem, you don't need to do this here. You can reference back to your first setup page. But just so you could see everything as we're drawing out our force and our free body diagram, I drew it on the same page again here. So I can look here, I have my damping, my spring, I have my external load, my mass, my displacements, my chosen coordinate system, x positive right, y positive up. Now I draw out just my mass, what forces are acting on this to draw out my free body diagram. Okay, here's my external load P of T, acting my positive x direction. Here is my weight force acting down, my normal force acting up at both of those wheels there, and I have my spring force over here acting in my negative x direction, and I have my damping force here acting over my negative x direction as well. And I've also included the inertia force right here, or mu double dot, or mass times acceleration there. So with this free body diagram, the next thing that we're going to want to do is come up with our equation of motion based upon what we drew here as our free body diagram. Move that up a little bit there. So F equals ma. Go back to that equation 2.3 from our textbook that they told us to use for this method. And we can find out is here, okay, my right-hand side of the equation, there's my mass times my acceleration there. My left-hand side is the summation of all these forces. And we're going to deal with the x direction on its own. We're not going to worry about our y direction yet. We're just going to deal with our x direction on its own here. So our weight force, or two normal forces, are not going to come into play right now. We're only going to consider our x direction forces here. So what do we have in the x direction? Positive external load. We have our damping force negative and our spring force negative as well. We can write that out. P of T minus our F of S minus our F sub D here is equal to the right hand side mass times acceleration, or U double dot. We can rearrange that now, solve for our P of T for external load. Mu double dot plus F sub S plus F sub D is equal to P of T. So the next thing we want to do is take a look at our spring force. So let's take a look there and recall that we have, okay, F of S equal to K sub S for our general equation here for a spring force. We want to relate it to our problem here where we have a moving base. So if we have a moving base here, we have the base moving this distance here, Z of T, and we have our mass moving this distance over here, U. So our distance, our S here, is going to be F of S is equal to K times U minus Z, our U minus our Z here. And again, this is because we have that moving base. So now that we have our F of S relationship, we now want to come up with our F of D, or our damper force relationship over here. So our damper force, F sub D, is equal to C times, and again, our moving base is U dot minus Z dot here. So now we have two expressions for F of S and F of D, our spring force and our damper force, that we can plug back in to our equation of motion that we solved for previously. So that's what we do down below here. We have these two expressions. We can plug them back in. So we plug those in here. We have mu double dot plus our F of S and our F of D is equal to this external P of T. So now we'll plug in our F of S here and our F of D right there. So here we go. I rewrote that equation here so we can start fresh on this page. We have our F of S here. Here's our expression for F of S we just solved for. Here's our F of D here, our expression for F of D here, spring force and damping force. Plug those two in, and we end up with this relationship here, mu double dot plus C times now U dot minus Z dot plus K times U minus Z is equal to our external load P of T over here. We can distribute our C and our K through here. We end up with mu double dot plus cu dot minus cz dot plus ku minus kz is equal to p of t. So from here, what we want to do is kind of rearrange and separate. So we have the equation of motion for the actual displacement of the mass relative to the inertial frame is what this is going to give us here in the end. We rearrange, separate. We have our u's on one side, our z's on the other side over here. We end up with mu double dot plus cu dot plus ku is equal to cz dot plus kz plus our external load p of t. So again, this is for relative to the inertial frame. So now that we've just solved for our equation of motion of the mass relative to the inertial frame, let's go back and take a look at the base motion equation in terms of displacement. So we want to look relative to the moving base in this case here. So relative displacement term, we have that this new term W is equal to U minus Z for our relative displacement over here. We can rearrange that, solve for our U. We find that U is equal to W plus Z, and rearrange this. From there, we can take the derivative and the second derivative of each of these. So our U dot is equal to W dot plus Z dot. Our U double dot is equal to W dot and Z double dot. So now we can go back to that previous equation of motion here, where we have our mu double dot plus cu dot plus ku plus cz dot plus kz plus pt, which is relative to the inertial frame. When I do it relative to the moving base now, we can plug in these relationships that we just found based off of relative displacement back into that. So we want to plug in, everywhere there's a u, we'll go w plus z. Everywhere there's a u dot, it'll be w dot plus z dot. Everywhere we have a u double dot, it would be a w dot and a z double dot. So we do that there. We can plug right back in. Okay, so we say, okay, we have a u double dot here. We can plug in this term. We have a u dot right there, so we can plug in this term here. Now we have right here next to our k, we have a u, so we can plug in a w plus z. Cz dot carries down, our kz carry down, pt comes down. What we can do now is start doing some cancellations. We can see, okay, on this side here, we have a cz dot. There's my cz dot there. I have a kz here. Here's my kz there. Cancel those out. Simplify this down a little bit. And as we simplify that down, cancel those out. And now see the next step here is we can distribute this m through. So now we have m double dot plus mz double dot plus cw dot plus my kw is equal to pt. I can rearrange these and separate these out again. And what we end up for our final answer for our relative displacement down here relative to the moving base for our equation of motion is mw double dot plus cw dot plus my kw equal to p of t minus my mz double dot. And again, this is for relative to the moving base rather than relative to the inertial frame.